Hi everybody, welcome back to Chem Help ASAP. In today's video, we are going to be talking about galvanic cells. Let's get started. Here is a very simple schematic of a galvanic cell. Now, in a galvanic cell, your current will always flow spontaneously. We will calculate this current, but in just a second. When we draw galvanic cells, we're always going to put the anode on the left and the cathode on the right. Now, the anode is where our oxidation occurs, and the cathode is where our reduction occurs. Both of these cells must be connected by some sort of salt bridge, and this is so we can have the exchange of ions. Now, the ions do move in very particular directions in a galvanic cell. Your anions are going to move to the left towards the anode, and your cations are going to move right towards the cathode. Your electrodes on each side may be made of a metal like platinum, or they might be made of the metal undergoing a reaction. Now let's take a look at a specific galvanic cell. Let's create a galvanic cell with silver and zinc. Here are our standard reduction potentials for both silver and zinc. Now, clearly, we cannot have both of these metals be reduced. Something is going to have to gain electrons, while the other is going to have to lose electrons. The question is, which one of these two reactions needs to be flipped to an oxidation? Well, the key is we are constructing a galvanic cell, which means current will flow spontaneously, which means when we calculate the E of this cell, it must be positive. Here is our equation for calculating E of the cell. It is simply the E of the reaction happening at our cathode minus the E of the reaction happening at our anode. So if E needs to be positive, then it is our zinc reduction which needs to be flipped to an oxidation. So our E cell is going to be the reduction of silver minus that of zinc. So I simply plug my standard reduction potentials in like so, and I get an E cell of 1.56. Let's write our balanced redox equation, and hopefully what is happening at each electrode will be a little more clear. Looking at our standard reduction potentials, we've already figured out we need to switch up zinc, but you can see our number of electrons is not equal. So I'm going to multiply my silver reaction by 2. Now it looks like this. Add it to my zinc. You can see I've switched my zinc from a reduction to an oxidation. And I simply add these two half reactions together. When I do that, you can see that my electrons add out, and I just bring everything else down. So my reaction for this galvanic cell is this right here. So my silver is going to be reduced to silver metal, and my zinc is going to be oxidized to zinc cation. Again, let's fill this in on our diagram. My anode is where my oxidation occurs. That is my zinc reaction. So I am going to make my electrode zinc metal, and as this cell runs, it will create zinc cations. Over on my cathode, that is where my reduction takes place. That is my silver reaction. So let's make this electrode silver metal, and my silver cations in solution are going to be reduced to form silver metal. Now, obviously, there are counter ions in solution. The identity of this matters less. You just need to make a salt that's soluble, so very often your counter ions will be nitrate. So your anode might have zinc nitrate, and your cathode might have silver nitrate. The other thing I want to write in is the current. So this is the current that I calculated from the E cell. So this galvanic cell will produce 1.56 volts. Let's take a look at a couple more galvanic cells. This problem reads, calculate E cell and write the balanced redox equation for a galvanic cell using the following half reactions. So again, we have been given reduction potentials for the following half reactions. Remembering, if we have a galvanic cell, that means that our E cell value will be positive. So here is our equation for calculating E cell. To get a positive value for E cell, our manganese must be the reduction and our sulfur must be the oxidation. So E cell is going to be 1.68 volts minus 0.2 volts. Our E cell is going to be 1.48 volts. Now let's write the balanced redox equation. Looking at my two reduction potentials, I will need to address the electrons. They need to be equal. I'm going to multiply my manganese half reaction by 2 and my sulfur by 3 to give me 6 electrons in both half reactions. I also am going to flip my sulfur reaction because I've already determined that it must be happening at the anode. It is going to be my oxidation. Okay, here is my manganese, again multiplied by 2. Here is my sulfur multiplied by 3, and you can see I have switched my sulfur. I now have electrons as a product. When I add these two half reactions, I get this as my overall balanced equation. Let's do a calculation with another galvanic cell in a slightly different way. This problem reads, a galvanic cell has an E cell of 3.42 volts. We are given the overall equation for this cell. The value of E for copper is 0.52, and we are asked to calculate the reduction potential for barium. We're still going to be using this equation right here for our calculation, but this time we already know what E cell is. Let's identify our cathode and our anode reactions. We're going to get this from our overall reaction. So you see my copper is going from +1 to solid, so it is being reduced just like it is written right here. My barium is going from barium solid to barium +2, so it is definitely the one being oxidized. Therefore, in my equation, my copper reaction is happening at my cathode and my barium reaction is happening at my anode. Now let's plug in my numbers. My E cell is 3.42 as given in my problem. The copper is 0.52 again as given in the problem, and I am solving for the barium. So my standard reduction potential for barium is negative 2.9 volts. I hope you found this video helpful, and thanks so much for watching.